Okay, so hi, we're back after a long time. So let's get on with it. I'll be recording this in the dark for some reason. But anyways, okay, so last time what we discussed was we were talking about buffer pool. What is a buffer pool? And we drew some analogies between buffer pools and the OS system called mmap, and how the two compare to each other, and why mmap is bad for you because then you start building this infrastructure which lightly is similar to what you'll be building in a buffer pool. So it's better to use a buffer pool rather than using mmap from your OS. So we saw that how buffer pool was a cache for your database disk pages that were lying on disk. And as you need the pages, you fetch pages from the disk and you bring them into the buffer pool, and then you hand the pointers back to the execution engine. The buffer pool obviously lives in the main memory, the RAM. So you don't have infinite main memory. So obviously you don't have infinite the buffer pools, and the storage is limited. So what you need to do is like any other limited storage, you need to evict pages. You need to evict pages depending on various algorithms that you use. So last time we discussed some algorithms. We'll quickly go over them. We studied the very first algorithm as least recently used, that you mark the timestamp that when that particular page was used, and depending on that particular timestamp, you decide that whether to evict the page or not. Then we saw the clock algorithm, where you start with the reference bit zeros and you maintain this logical clock which goes around all the pages, and as it finds any page that was not accessed last time it came around, it swaps the page out. If it finds any reference bit that is set to 1, it will turn it back to 0. So we saw clock algorithm. Then we discussed that these two methods are susceptible to something known as a sequential flooding. So what is a sequential flooding? But before we get to sequential flooding, we also let's take a step back and think about these two algorithms that clock and least recently used give you some idea of as to when page was last accessed. They give you some estimate of the time. It doesn't give you an estimate about how many number of times that page was accessed. So it takes into account the recency of accesses, but it does not count the frequency of accesses. So if you're designing a good algorithm, you always need to keep in mind that you need to keep both factors accountable, recency and frequency, to develop a good page replacement algorithm. So apart from the recency and frequency debate, there is something known as a sequential flooding, where one query comes along and it does a blind scan on your whole table, and it brings in a bunch of pages which are just going to be used once and not going to be used again. So what happens is when you are bringing these one-off pages that you're going to use once, you might swap out some useful pages that are being used by some other queries, and which are hot. So we saw that page 0 was being used, but due to the query 2, that is a sequential scan, you're bringing in pages and you're pushing that page 0 out. But that page 0 is being used by this very first query, which is a query that occurs very frequently. So what you'll have to do is you'll again take page faults. So they're not called page faults in database terms, but you know what I mean. Like you'll decide that this page is not there, and then you'll just tell your storage manager to get that page for you. So that's extra CPU cycles that you're wasting. Okay, so in OLAP workload, what you want to use, you want to use the most recently used. Why? Uh, because it is very highly probable that once you have done a analytical query, it is very unlikely that you will be running that query again. So once you have fetched the data, you are not going to, like, once you have gotten the data, you can, on your application side, you can run your own Excels and Tableaus to build dashboards. But it is very highly unlikely that you'll run the same data warehousing query again and again. So you just assume that all the pages are one-offs, that you are bringing one page in and you just uh, the very recent page that you have fetched is very highly unlikely to be used again, so you can swap it out. I hope that made sense. So I rushed a bit, but sequential flooding, then we see that we saw that there is an algorithm called least frequently used that gives you some estimate as to when that how many times that page was accessed. So, but this also carries some complexities, like it has a logarithmic implementation that you have to maintain some sort of structure in memory, like a priority queue, or you have to, whenever you want to evict a page, you have to sort on based on the number of times that page was accessed last. So you might want to use a priority queue for this, but that still entails a login time. So that still has logarithmic complexity. So not very cheap. And what happens is that this least frequently used just totally ignores time. So the very second point that is written there is it ignores time and accumulates stale pages with high frequency count. So let's say that I gave this example last time also that imagine I wake up one night and I want to access some particular page a million times, and then I go back to sleep. Then my users wake up next morning, and if I'm running a least frequently used algorithm, then what I'll do is I'll look for pages that have been least frequently used, and I'll swap those out. But the page that I read a million times midnight will never be used again because it was a one-off. Like I was, it's a Yeah, so I woke up in the middle of the night. I accessed some account and it accessed some page, but I accessed that account like a million times. So that particular page has account set to 1 million now. But the next day, no one is accessing that particular account again. So that just leaves a page with a very high frequency, but it is of no use to other users. So yeah, useless pages with very high frequencies get accumulated with over time. That's what the statement says. I hope that also made sense. I also rushed through that also. Okay. So then we got to LRUK. Now what LRUK does is MS SQL uses it, Microsoft SQL Server. And what LRUK does is it tries to give you some balance between frequency and recency. So you maintain k slots of last access timestamps. So you're maintaining timestamps that gives you some sense of recency, and you maintain k number of them. So that particular K is defining your number of frequencies, like how many times that particular page was accessed. So it tries to balance between both frequency and recency. So we saw an example that if K is equals to 2, then you store some particular time, and we did a walkthrough on this that when it is accessed, then you update the timestamp. Then you want to evict a page, then you consider the timestamp which is furthest away from the current timestamp to evict, and you just treat this empty slots at infinity. So we did a whole walkthrough in the last video, so you can go and watch. I hope no one is watching though. Okay, so after LRUK, what we did was MySQL's approximate LRUK. So what this does is it tries to give you some sense of recency as well as frequency. So how does it give you some sense of recency? It maintains a linked list like LRU, like least recently used that we saw in the very first algorithm we saw. We maintain a linked list and we move pages around. And how does it give you? Gives you some sense of frequency. It maintains two portions of the linked list, where one is a young portion and one is the old portion. So the old portion contains pages which have not been used very frequently. So once your page has been accessed enough time, you move it to the front of the list, to the new list, and there that gives you some sense of frequency for that particular page. So yeah, as we can see, like the two algorithms that we covered, that the databases use, like MySQL and MS SQL, LRUK and approximate LRUK, are just trying to balance between frequency and recency. Like they want some sense of both of them. So what we are going to cover today is something known as ARC. ARC stands for adaptive replacement cache, I guess. Wait, let's look up. Yes, adaptive replacement cache. So I was searching about this, and whatever I found on YouTube was related to ZFS, like this particular file system. Okay, so let's start explaining this ARC protocol. So what you have in ARC protocol is you maintain four lists and a parameter called P. So there is a recency list that gives you some idea as to when pages were last accessed. Then you have ghost list for that particular recency list. You have T1, which is your recency. Then you have B1, which is your ghost for recency list. That is that pages that were in T1 but now they are not. Then you have T2, which is your frequency list that once pages are in recency list and they get accessed again, they are moved into T2. That is the frequency list because their frequency has increased. Then you have a ghost list for the T2 as well for the frequency list. Then you have a size parameter P, which adjusts that how many. So assume that this is assume that this is some portion of RAM, and we have divided this portion into T1 and T2. There is a parameter P which is deciding as to which particular list should hold more pages or should be allocated more memory. If you are taking heavy cache misses on recency list, then you favor that recency list and you increase the P because P is the ratio of T1 to T2. So if you increase P, that means you're increasing T1, right? So if you are taking a lot of hits on the pages that should be in T1, then you increase the particular P parameter. If you're taking a lot of hits on the pages that should be in T2, but they are not, then you decrease the parameter P. That's obvious. Like if P decreases, then T2 increases. Like the denominator is bigger. But anyways, let's get on with it and let's see how it works. So let's do a walkthrough. Let's say we have a page and this is the lookup protocol that when you're looking up a page, how do you go about and find a page? So what you do is in the beginning of the life cycle, all the pages that are brought into memory are put in T1, the recency list. So all the pages are lying in T1. When you access a page, the page is moved from T1 to T2. Now, because it has been accessed more than one time, so it moves to the frequency list. So you found the page in T1 and you just moved that particular T1 to T2. Now we'll take another scenario that you did not find it in T1 and you found it in T2. So what you do is you do nothing. So the page is lying in the frequency list. You just accessed it again. So you don't do anything because it maintains its frequency status. So it's enforcing its frequent status that the page has been accessed again. Now, let's assume you did not find the page in T1. You did not find the page in T2. What do? You go to the B1, the ghost of recency list. If you find that page there, so you realize that the page is lying in the ghost list of the recency list, but it should have been in the recency list. So what do? You increase the parameter P. So you increase the size of P in favor of the recency list so that the recency list can hold more pages now. And you move the page to T2 because it has been accessed again. Because now you don't move it to T1, you move it to T2. Now let's assume that you did not find the page in B1 as well, and you went to B2. So what if you found the page in B2? What that says is that particular page should have been in the frequency list in T2. So you decrease the parameter P to favor that particular T2 queue, the list T2, and you increase the size of the T2. So you move the page back to T2 because you are accessing again. So you move the page back. So as you can see that whenever you are accessing a page, you're porting the page back to T2. But if you are loading that particular page from the disk, that if that is a new page, you put it to T1 because that is the very first time you are accessing it. Like it's the very first time that you have accessed that page. So you put it to T1. You don't put it into T2. But if you access that particular page again, then you move it to T2 again. So okay, so I might have been very fast here, but if you have to take away something, that then you can take away the fact that the parameter P maintains this particular ratio between the frequency list and the recency list, and pages keep jumping between these two. And you have a ghost list, which tells you that pages should have been in the actual queues, but they're not. And that serves as a tweaking parameter for maintaining that P which you are. So what happens is that if you are taking a lot of hits on pages that should have been most recently used, then the expectation is that this arc algorithm will automatically increase your P and you'll have more recent pages. So it tries to balance between recency and frequency while maintaining a ton of infrastructure, like you're maintaining four queues and a parameter P itself. So yeah, we'll just cover this for this time. My earphones battery is low and I have to sleep. We'll go over this again in the next lecture that what we did. And I think I was reading it very fast, like I was rushing it through. So I'm sorry for that. But yeah, it's a beautiful protocol. The R protocol is very beautiful. It tries to give you uh, dynamic parameter P, which automatically adjusts according to where you are actually getting cache misses. If you are getting a lot of cache misses in the frequency list, it will just increase the capacity of the frequency list. If you are getting a lot of cache misses in the recency list, it'll just increase the frequency and it will just dynamically keep updating your caches. It's a beautiful algorithm, and yeah. So I'll see you next time. Thank you.